Hello, everyone. So today we want to do just some sample questions or practice questions, basically, from all the topics together. So I asked you if you have any specific questions. I haven't received any particular questions sent by you guys, so just let me do some random questions then. So this one, we'll start with page 71, question 27. For each part, determine the truth value. Justify your answer. Part A, for each n there exists m such that n squared is less than m. So for this type of question, if you remember, we said that, why don't you think about some examples to get some idea about the statement, whether is true or false. So for example, we want to know whether for each n there exists m such that n squared is less than m or no. Well, why don't we start with some n? Let's say if n is 2, for example. Then can we see that there exists m such that n squared, which will be 4 is less than m? Can we say that there exists some m that n is bigger than 4? Of course. We can choose, for example, m to be 5. 5 is bigger than 4. Or let's say, for example, if n is 3. Then can we say that there exists some m that 9 is less than m? Again, of course, we can choose m to be 10, for example, and 10 is bigger than 9. And so on. Right? So it seems that, any n that I choose, there exists at least one m. In fact, it seems that there exists infinitely many m values that m is bigger than n squared. So, these are examples. We cannot give examples as proof. This is just in our rough worksheet in order to get the idea for this question. It's not a part of solution though. But the idea says that, for example, if n was 2, we chose m to be 5, which is bigger than 4. Or if n is 3, then we chose m to be 10, which is bigger than 9, and so on. So in general, for any given n, what can we choose as m? By the way, the domain is mentioned to be set of all integers. Suppose that the domain is the set of all integers. So that means our values, our parameters, variables are chosen from Z. So given n, the statement is true because given any n in Z, we can choose m to be n squared plus 1, which also belongs to Z, of course. If n belongs to Z, n squared plus 1 for sure also belongs to Z. Then we will have m, which is n squared plus 1, bigger than n squared. So that means, for every n in z, there exists m such that n squared is less than m. You wanted to choose at least one m value that is bigger than n squared, and we did that. The m value that we chose was n squared plus 1. All right. Part B, there exists n such that for each m, n is less than m squared. There exists n such that for each m, n is less than m squared. Again, before deciding whether it's true or false, let's try to get some idea about this by thinking about some examples or some numbers. Let's say, for example, if n is 5, can we say that 5 is less than m squared for each m? Well, is it true? It's not true because, for example, m equals 1. If m is 1, then 1 squared is not bigger than 5. So, for example, for n equals 5, this is not true. What about for n equals 6? 6 less than m squared. Again, not true because, m equals, again, 1 squared is not bigger than 6. So for 5, 6, 7, and so on, this is not true. But what about numbers before 5? So for example, 4 less than m squared. Again, this is not true for every m. Again, m equals 1 does not satisfy this. 3 less than m squared, not true for everyone. 2 less than m squared, not true for everyone, every m. 0 less than m squared. Again, not true for every m because m equals 0 does not satisfy this. 0 is not less than 0. But remember, my domain is supposed to be set of integers. So I can also choose numbers from set of negative numbers. For example, -1. Can we say that -1 is less than m squared for every m? Well, this one is true. -1 is less than m squared for every m. Well, that's it. We wanted to choose because the question was asking whether there exists n. There exists n means, can we say that there exists at least one n such that n is less than m squared for every m? Well, we tried many n values. We observed that we cannot choose n to be any positive number or even 0. But if we choose n to be a negative number, for example, -1 or -2 or any negative number, then -1 is less than m squared for every m, because for every m squared is, of course, non-negative, and therefore any non-negative number is automatically bigger than -1. So we can say that this is true. Because we were looking for at least one n value and we found it. True set n equals -1, then we can say -1 is less than m squared for every m in z, since m squared is bigger than or equal to 0, which itself is bigger than -1 for every. This is true even for every real number, and of course this is true for every integer m. as well. So we showed there exists n, which is n equals -1, such that n is less than m squared for every m in Z. Okay, let me also do part F. Part F says there exists n, there exists m, such that n squared plus m squared equals 6. Well, this basically is asking us whether this equation, this given equation, has any solution in the set of integers. Because if it has a solution, solution means what? Means at least one n value and one m value. There exists at least one n value and one m value such that n squared plus m squared equals 6. And this is exactly what the question is asking us. So if the equation is just like solving the equation, if the equation has a solution, means there exists at least one n value and one m value, that n squared plus m squared equals 6. But if the equation has no solution, means there does not exist any n and m value such that n squared plus m squared equals 6. Okay, so here we want to know whether n squared plus m squared equals 6 has any solution in the set of integers Z, in the set Z. Well, how can I solve this equation? Please note that first of all, n squared and m squared, both of them are non-negative, so they're at least 0. And for most numbers, for most integers, n squared plus m squared is bigger than 6. Because, for example, even if one of n or m is at least 3, then n squared or m squared will be at least 9, plus another number will be bigger than equal to 9 and bigger than 6 for sure. So for most integers, n squared plus m squared is bigger than 6, and therefore cannot be equal to 6. There are only few cases where n squared plus m squared would not exceed 6, and we can check those one by one. You can check those one by one. The cases where n squared plus m squared does not exceed 6. And that's it. If we check those one by one and none of them equals 6, and for those cases, then that means this equation has no solution. So let's say, let me write it this way, that if n is bigger than equal to 3 or m is bigger than equal to 3, then n squared plus m squared will be bigger than equal to 9. And therefore n squared plus m squared will be not equal to 6, because if something is bigger than equal to 9, then it won't be 6 for sure. And otherwise, if n is less than 3, I mean, this one, like, by the way, I mean in absolute value. because the square of a number depends on the absolute value of that number. Because power 2 kills the sign, right? So if absolute value of n is bigger than or equal to 3, then n squared will be bigger than or equal to 9. And if absolute value m is bigger than or equal to 3, then m squared will be bigger than or equal to 9. And in any of those cases, n squared plus m squared will be also bigger than or equal to 9. Otherwise, if absolute value n is less than 3 and absolute value m is less than 3, meaning that because these are integers, so something less than 3 in absolute value means less than or equal to 2. And this means n is between -2 to 2. Or let me write it this way. And this means absolute value n equals 0 or 1 or 2. And absolute value m equals 0 or 1 or 2. Then we can say that n squared plus m squared equals, so what will be the possibilities? If both of them are 0, there's just few possibilities, right? We can check them one by one. If both of them are 0, then the addition will be 0. If one of them 0, one of them 1, the addition will be 1. If both of them are 1, then the addition will be 2. Right? If the first one is 1, second one also 1, the addition will be 2. If one of them 1, one of them 2, if one of them is 2, then the square of that guy will be 4 plus 1 will be 5. Or the other possibility is that one of them is 2, one of them is 0. So then I'll get 4, because if one of them is 2, then the square of it will be 4. If one of them is 2, one of them 1, the square addition of them will be 5. And if both of them are 2, then the addition will be 8. So 0, 1, 2, 4, or 5. So 3 and 6 are not covered. 3 and 6 and 7 is also not covered, but we're only interested in 6. We want to know whether n squared plus m squared can be equal to 6. So in this case, so again, in this case, n squared plus m squared equals 6 has no solution. So in case 1, we basically divided all possible cases into 2 cases. We have 2 numbers. Either at least one of those 2 numbers has absolute value bigger than or equal to 3, which we covered in case 1, or both of those numbers have absolute value less than 3, which we covered in case 2. Either in case 1 or case 2, n squared plus m squared cannot be equal to 6. So overall, n squared plus m squared equals 6 has no solution. Either in case 1 or case 2 above. So we can say that the given statement is false. We wanted to know whether there exists n and there exists m that n squared plus m squared equals 6, but we showed that there does not exist any n and m value such that n squared plus m squared equals 6, because this equation has no solution. Okay, guys. Okay, guys, next question. This is page 95. Question 8. Prove that if n is a perfect square, then n plus 2 is not a perfect square. So we want to show that n plus 2 is not a perfect square. So why don't we assume that n plus 2 is a perfect square and then try to reach a contradiction? So proof by contradiction. In proof by contradiction, we assume what we want to show is wrong, and then we reach a contradiction. Here we want to show that n plus 2 is not a perfect square. So let's assume n plus 2 is a perfect square and then reach a contradiction. So suppose that, proof by contradiction, suppose that n plus 2 is a perfect square say n plus 2 equals L squared for some integer L. Here we also have n equals k squared for some integer k. Because remember, our assumption is that n itself is a perfect square. It says if n is a perfect square, then n plus 2 is not a perfect square. So we're assuming that n is a perfect square, and we want to show n plus 2 is not a perfect square. We assume it is n plus 2 is a perfect square. So we wrote it as L squared. But my assumption is n itself is a perfect square. So I can write in the form of k squared. So it's important here that you use a different letter here, because I already wrote n plus 2 as L squared for some L, because I'm assuming that n plus 2 is a perfect square. N is also assumed to be a perfect square. So that can be also written in the form k squared, but please use different letters. So do not use L again, because if you use L squared for both for n plus 2 and also n, implicitly you're assuming that n plus 2 and n are the same number. And of course, that's not true, right? So in mathematics, to write in general, we have to use different letters, unless we know that, for example, two quantities are the same, then we can use the same letter, but otherwise we have to use different letters. So n equals k squared. Then if I replace n with k squared into this equation, then what do I get? I'll get k squared plus 2 equals L squared. And then that means 2 is equal to L squared minus k squared, which means L minus k times L plus k. And then this means 2 is equal to, okay, now I have product of two numbers equals 2, and both those numbers are integers. So when can I say that product of two integers is 2? If one of them is 1, one of them is 2, or one of them is minus 1, one of them is minus 2. So I can say 2 is equal to L minus k, 1 equals L plus k, or 2 equals L plus k, 1 equals L minus k, or minus 2 equals L minus k, minus 1 equals L plus k, or minus 2 equals L plus k, minus 1 equals L minus K. One of these four possibilities must happen. So here we use the fact that if product of two integers is 2, then either one of them is 2 and the other one is 1, or one of them is minus 2 and the other one is minus 1. 2 is a prime number, so it cannot be written as a product of two integers where none of them are 1 or minus 1. So the only way to write 2 as product of two integers is either 1 times 2 or 2 times 1, or minus 1 times minus 2 or minus 2 times minus 1. Now we can easily check that none of these four equations has any solution in the set of integers. So let's call this one equation 1, equation 2, equation 3, equation 4. So let's look at equation 1 now. Equation 1, if I add both equations, then 2 plus 1 is 3. 3 will be equal to 2L. And that means L equals 3 over 2, which does not belong to Z. So that means equation 1 has no solution in Z. Because when we add them, we get L equals 3/2, but it must be integer. So equation 1 has no solution in Z. Similarly, equation 2, equation 2, 3, and 4, none of them have any solutions, have no solutions, have no solution. In Z. So that means, so that's basically our contradiction. Because we assume that there exists some L, that n plus 2 is L squared, but we reach a contradiction. We show that there is no L, because there was no solution for L or K in any case. Okay, this contradiction shows that the statement that we wanted to show, this contradiction shows that if n is a perfect square, then n plus 2 is not a perfect square. Okay, let's look at the next example. Question 44, page 163. Let f of x equals x squared. Find f inverse of this set x such that x is bigger than 4. So this question is about f inverse of a set. F inverse of a set can be defined even if the function is not invertible. F inverse of a number can be defined only if it's invertible, and f is invertible if it's 1 to 1. But f inverse of a set can be defined for any function, basically. So recall that F inverse of A is equal to the set of X such that F of X, or I can say F inverse of, let's say, S. Let's say, for example, F is from A to B. So this is, let's say, A, this is B. And if S is somewhere here, F inverse, a subset of B, basically, F inverse of A is the set of all elements in A that are going to be mapped into S. So all elements X in A such that F of X belongs to S. If an element in A is mapped into S, then that element is in F inverse of S. So F inverse of S is a set. S is a set, is a subset of B. F inverse of S is a subset of A. Which subset of A? The set of all elements in A that are going to be mapped into S. So you have to look at elements of A. Look at elements of A. If a particular element is mapped into S, that element will be inside F inverse of S. Otherwise, it's not inside F inverse of S. So here, you want to find F inverse of this set X X such that X is bigger than 4. So this one, by definition, we can write it as set of all elements in the set of real numbers such that F of A is bigger than 4. Right? In order to find out about this set, we have to look at elements in the domain, which is R here, and look at F of those elements. If F of those elements is inside this set, when can I say that something is inside this set? If an element is bigger than 4, then that means that element is inside this set. So I have to look at F of A, look at different A values in R, and look at F of A. If F of A is bigger than 4, then that A is inside this set. Otherwise, A is not in this set. So we can say that this set here can be written as set of all elements A in R such that F of A is bigger than 4. F of A is bigger than 4 means what? What is F of X? F of X is X squared. So F of A means A squared. So we want to have A squared bigger than 4. And A squared bigger than 4, if you take square root from both sides, square root A squared is absolute value A bigger than 2. And absolute value A bigger than 2 means A is bigger than 2, or A is less than minus 2. Absolute value of a number bigger than 2 means that number is bigger than 2, or that number is less than minus 2. Well, that's it. So we can also write this in an interval notation. We can also write it as minus infinity to minus 2, union 2 to infinity. So this is the answer for F inverse of this set. So F inverse of a set is a set inside the domain, the set of all elements in the domain that are going to be mapped into S. Let's look at one more example from this topic. So let's say if you want to show that, so question 46, let's say, question 46. So let F from A to B be a function. Suppose that S and T are subsets of B, so S and T subsets of B. Show that F inverse of S union T is equal to F inverse of S union F inverse of T. Okay, so how can we show that two sets are equal to each other in mathematics and in set theory? How can we show that two sets are equal to each other? Well, we have to show that the first set is a subset of second set and second set is a subset of first set. So we have to show, need to show F inverse of S union T is a subset of F inverse of S union F inverse of T. So let's call this one 1. And second condition we need to show F inverse of S union F inverse of T is a subset of F inverse of S union T. Now to prove 1, how can I show that one set is a subset of another one? We have to take an element in the first set and show that that element must be in the second set. So let A, let's say inside F inverse of S union T. Then what can I say? Then we can say that F of A must be inside S union T by definition of F inverse of a set. F inverse of a set, remember we defined it here. F inverse of a set is a set of all elements inside the domain such that F of those elements is inside S. So if small a is inside F inverse of S union T, then F of A must be in S union T. So we can say F of A belongs to S or F of A belongs to T. Now, if F of A belongs to S, what does that mean? That means A belongs to F inverse of S. Because A belongs to F inverse of S is same as saying that F of A belongs to S. And this one means A belongs to F inverse of T. So that means A belongs to F inverse of S union F inverse of T, right? If A belongs to one set or A belongs to the other set, then we can say that A belongs to the union of those two sets. So this was proof of 1, right? Proof of 1. We took some element A in the left-hand side, and we showed that A must be in the right-hand side as well. And similarly, we can prove 2. The proof of 2, it will leave as exercise, is similar to above. And 1 and 2 together will imply that F inverse of S union T equals F inverse of S union F inverse of T. Okay. Okay, next question. Question 18. Question 18, page 186. Suppose that A and B are two sets such that cardinality A equals cardinality B. Show that cardinality of power set of A is equal to cardinality of power set of B. There is a common mistake here. Some people say that, well, if A and B have same cardinality, let's say both of them have cardinality equals n, then cardinality of P of A, the set of all subsets, will have 2 to the power n elements, and P of B also has 2 to the power n elements, and therefore the cardinalities are equal. But that's a correct argument as long as A and B are both finite sets. But the question is not saying or not assuming that A and B are finite sets. So of course, if A and B are finite sets, then this will be obvious. But the interesting thing is, even if A and B are not finite, still the statement is true. So please recall that when can we say that two sets have equal cardinality? So recall for two sets A and B, we have cardinality A equals cardinality B if there exists a bijection. Bijection means a one-to-one function, which is also onto. Function f from A to B. So if there is a bijection from A to B, then we say that A and B have equal cardinality. This definition is valid regardless whether A and B are finite sets or infinite sets. So here this is my assumption that there is a bijection from F from A to B, and I want to show that cardinality P of A equals cardinality P of B. Therefore, I have to construct a bijection from P of A to P of B. So our goal here is to construct a bijection, let's call it curly F, from P of A to P of B. We construct F, curly F, as follows. So I want to define a function from P of A to P of B. So the input for this new function must be some element in P of A. Some element in P of A means a subset of A. Because P of A is a set of all subsets of A. So some element in P of A means a subset of A. So curly F on some element, let's say C. How am I going to define it? I'm going to define this as the set of all elements of the form F of small c, such that C belongs to capital C. For any, so this one here, let's say this way, that C here, capital C, is a subset of A. Okay, so see, this is A. This is A, this is B, and this is C here. And this one is a subset of A. Remember, we had a function f from A to B. this f here, f from A to B is a bijection. It exists since cardinality A equals cardinality B by assumption. So we already know that we have a function f from A to B, which is a bijection. I want to define another function. I call it curly f from P of A to P of B. So an input for this function will be a subset of A, because an input should be an element of P of A. Element of P of A must be a subset of A. So curly f on C, I'm going to define it as this set here. Set of all f of small c where C belongs to capital C. Every element of capital C, which I call it denoted with small c, is of course an element of A, because C is a subset of A. And if I have an element of A, I can apply f to it, and I will get an element of B, because remember, f is a function from A to B. So this set that I define, f of C, where C belongs to capital C, this is a subset of B. So far so good. Every element of P of A, if I apply curly f to it, I'll get some element in P of B, because I'll get I get a subset of B. Okay. So now we have to show, I need to show that curly f is 1-to-1 and is onto. So how can I show these two things? So first of all, let's show that it's onto, to show curly f is onto. So let's take some subset of B. Let's say D as a subset of B. I have to show that this D is the output for some input in P of A. So need to show D is equal to P of curly F of C for some C. So I'm going to consider C to be the set of all elements of the form F inverse of D, where D belongs to D. Then what will be curly F of C? Then curly F of C, by definition, how can I find curly F of some set? I need to apply small f to every element of that set. So I need to apply small f to every element of this set, which is like F inverse of D. D belongs to D. And F of F inverse is the identity. F of F inverse of D is same as D. So this is same as set of all elements D such that D belongs to D, and of course this is same as D. So what did we show? We showed that for any D as a subset of B, there exists C as a subset of A, such that curly F of C is equal to D. And this means curly F is onto. The function is onto because any element that I consider inside codomain, what is the codomain here? Codomain is P of B. Any element that I consider inside codomain means any element of P of B. Any element of P of B means an arbitrary subset of B. If you want to consider an arbitrary element in P of B is the set of all subsets of B. That means you're considering an arbitrary subset of B. I called it D. For any arbitrary element inside codomain, I found one element inside domain. Element inside domain here is C. It's inside the domain because it's a subset of A, therefore is an element of P of A, such that F of C is D. So every element in codomain, I found one element in domain, such that F of that element in the domain will give me the element in codomain. That means every element in codomain occurs as an output, and therefore the function is onto. Now, next we have to show that our function is one-to-one. So to show it's one-to-one, I'm going to do it this way, that, let's say C1 and C2 be two elements in P of A with C1 not equal C2. We will show that curly F of C1 is not equal to curly F of C2. So one way to show that a function is one-to-one is to show that if I consider two distinct elements in domain, they're going to be mapped to necessarily two distinct elements in codomain. That means the function must be one-to-one, because if a function is not one-to-one, then at least two different elements in domain will be mapped to the same element in codomain. So if I can show that whenever I consider two distinct elements in domain, they are for sure going to be mapped to two distinct elements in codomain, that means the function must be one-to-one. Now, if C1 is not equal to C2, C1 and C2 are two sets. Remember, C1 and C2 are elements of P of A. Therefore, they are subsets of A. So therefore, they are sets. Now, by assumption, C1 is not equal to C2. So that means there exists some C, which is in C1 and C not in C2. With C not belong to C2, or there exists some C in C2 with C not belonging C1. One of these two will happen for sure. If two sets are not equal, either first set is not a subset of second, or second set is not subset of first. So either one element I can find in first set, which is not in second set, or one element I can find in second set, which is not in the first set. So let's call this one possibility 1. And this one too. In 1, let's look at F of C1. F of C1 capital C1 is f of, let me call this element, maybe I can call it alpha because I called arbitrary element of these sets as small c. Let's call this one alpha. So this is f of small f of c, where c belongs to C1. And f of C2 similarly is f of c, where c belongs to C2. Now, f of alpha, I want to say that f of alpha is in f of C1. Now note, f of alpha is in f of C1 because alpha is in C1. And f of alpha is not in f of C2. Why is f of alpha not in f of C2? Since otherwise, means if f of alpha is in f of C2, then we can say that f of alpha equals, let's say, f of some beta for some beta inside C2. Because clearly f of C2 is the set of all elements f of C where C is in C2. So if f of alpha is inside f of C2, that means f of alpha must be equal to f of beta for some beta in C2. But f small f is 1-to-1 because it's a bijection. Small f is a bijection, therefore it's 1-to-1. Now, if you have a 1-to-1 function and f of alpha equals f of beta, you learn in high school that for a 1-to-1 function, if f of alpha equals f of beta, then alpha must be equal to beta. So small f is bijection by assumption, and therefore it's 1-to-1. So we can say alpha equals beta, and beta is in C2, so alpha must be in C2, and this is contradiction with alpha not in C2. Remember, alpha was supposed to be not in C2 in case 1. So we showed that f of alpha is in curly f of C1, and f of alpha is not in curly f of C2. So I found one element which is in curly f of C1, but not in curly f of C2. That means curly f of C1 as a set is not equal to curly f of C2. If you have two sets, and I found one element which is inside the first set, not inside the second set, well, then those two sets cannot be equal. Similarly, in case 2 above, you can show that curly f of C1 is not equal to curly f of C2. So that means curly f is 1-to-1. So we show curly f is 1-to-1 and on 2. So that means curly f is a bijection. And that means cardinality of P of A, curly f was from P of A to P of B, right? Is a bijection. So that means cardinality P of A equals cardinality P of B. If I find a bijection between two sets from one set to another, that means that the cardinality of those two sets must be equal. And this was exactly what we wanted to show. So we proved that. See, we didn't make any assumption about A or B being finite. We just used the fact that cardinality A equals cardinality B, which means there is a bijection small f from A to B. We used that bijection, which was given in the assumption, in order to construct a new bijection, which we called it curly f, from P of A to P of B. And once we constructed this bijection, we immediately concluded that cardinality P of A equals cardinality P of B. So we suggested a definition for this bijection, this curly f. We provided a definition, and then we showed that that definition that we suggested above is actually a bijection, meaning that it's one-to-one and onto. Okay, so we showed this bijection, and therefore we concluded cardinality P of A equals cardinality P of B. Okay, now let's look at the next question, page 301, question 17. I want to add one part to it. So let's say part A, true or false. Justify if x squared is 1 mod, let's say n, for some positive integer n, then x is 1 mod n or x is minus 1 mod n. Do you think this is true? Well, of course, the converse is true. If x is 1 or minus 1 mod n, then x squared will be 1 squared or minus 1 squared mod n, which will be 1. But the non-trivial part is the converse. If x squared is 1, can we say x is 1 or minus 1? Well, you know, for true or false questions, first you can try to construct a counterexample and see if you couldn't construct a counterexample and you wanted to show that it's correct, then of course you have to prove in general. But before trying to prove in general, we can always try to construct a counterexample first. And in this case, let's say, for example, if n is 8, this statement is false. Set n equals 8, then and x equals 3, then how much will be x squared? X squared will be 9, which will be 1 mod 8. But 3 is not 1 mod 8, and 3 is not minus 1 mod 8. So I found a number, which is 3, x equals 3, and n equals 8. And 3 squared is 1 mod 8, but 3 is not 1. 3 squared is 1 mod 8, but 3 is not 1 mod 8, and 3 is not minus 1 mod 8 either. So in this case, we constructed the counterexample that we were looking for. Okay, so this, of course, doesn't mean that this is the only example that you could provide. Of course, there are many examples for n and x. Depending on the n value that you use or choose, you can choose different x values. Of course, not all n values or all x values would work, right? For example, if for n equals 8, if I chose x equals 2, 2 squared is 4, which is not 1 mod 8. So I couldn't use x equals 2 or x equals 5. Or I couldn't use x equals 1 either, because I want to show that this statement is false. So I am looking for a number x which is not 1 or minus 1 mod n. So of course, I'm not allowed to choose, in order to construct a counterexample, of course, I'm not allowed to choose 1 or -1. And many other numbers won't work either. So of course, not every number would work, but what I'm saying is that this is not the only example that we could consider, we could construct. There are many other examples that you could construct, as long as you construct a number n and x such that x squared is 1 mod n, and x is not 1 or -1 mod n, then that's okay. All right, now part B, again, true or false. Part B, true or false. Justify. If x squared is 1 mod p for a prime number p, then x is 1 mod p or x is -1 mod p. Again, of course, you can first try to construct a counterexample. Here, p must be a prime number, so I cannot choose n equals 8 anymore, as I cannot use this counterexample anymore. P here must be prime, so you can see if p is 2 or p is 3 or p is 5. So for example, p equals 5. Which number squared will be 1? If p is 5, then 1 squared, of course, is 1. 4 squared is 16, which is also 1 mod 5. But can I consider 4 as my counterexample? We cannot consider 4 as the counterexample because 4 is -1. Well, 4 is same as -1 mod 5, right? 4 mod 5 is -1. So if you want a counterexample, x cannot be 1 and x cannot be -1. But 4 in this case is -1 mod 5. So we cannot use 4 as a counterexample. So if you try different p-values here, different primes, you can see that it seems that it's not possible to construct a counterexample. So our guess is that this statement is true. But remember, if you want to show that something is true, you have to prove in general. You cannot prove something is true with examples. Your proof has to be valid in general for every prime number p. So let x squared be equal to 1 mod p. Then we can say that p divides x squared -1. This is the meaning of congruent, two numbers being congruent to each other. Mod p, that means p divides the difference between those two numbers. And that means p divides x -1 times x plus 1. Now, we know that if p is a prime, write it this way, we know that if p is a prime number, then p divides ab implies that p divides a or p divides b. I think my screen was freezed for a second. So p divides x -1 times x plus 1. And we know that if p is a prime, p divides ab implies p divides a or p divides b. That's a feature of prime numbers. That if a prime number divides product of two numbers, then it must divide at least one of them. This property does not hold if p is not prime, but if p is prime, p divides ab implies p divides a or p divides b. Now, hence, in above, we can say that P divides x minus 1 or P divides x plus 1. Now, P divides x minus 1 means x is 1 mod P, right? X congruent 1 mod P is same as saying that P divides x minus 1. And similarly, P divides x plus 1 is same as saying that x is congruent minus 1 mod P. Okay, so we showed that if x squared is 1 mod P, then x is 1 mod P or x is minus 1 mod P. Okay.